This video teaches you how to use Python code to calculate value at risk with the variance-covariance method using the keyboard without touching the mouse. Please like, subscribe, and buy my books. Links in the description below. Let's get into this phenomenal video. To open Google Chrome, I press Windows key, D as in Delta, press the N key, press Enter. Alt E as in Echo, B as in Bravo. To pull up my bookmarks, press End, press Enter. Tab over till I get to value at risk. And this is the value at risk code. First of all, you need to install Yahoo Finance, Y as in Yankee Finance. To do that, just type pip install Y as in Yankee Finance. Control Enter to run that. And you can see the requirements already satisfied for me. I'm going to import several add-ins that I need to run this value at risk calculation with the variance-covariance method. So I'm going to import Y as in Yankee Finance as Y as in Yankee, F as in Foxtrot. Import NumPy as N as in November, P as in Papa. Import date-time as D as in Delta, T as in Tango. Import matplotlib.pyplot as P as in Papa, L as in Lima, T as in Tango. Then finally from scipy.stats, I'll import norm for the normal distribution. Control Enter to run this. Next, I'm going to create the portfolio. We're going to have 10 stock tickers. You can see them here on the screen in the portfolio, and they're going to be equally weighted. So to create a mutable list of tickers, I'll create the variable tickers and set it equal to a mutable list with 10 arguments. And I have each of the tickers I want. Companies like Apple Computer, Meta, Microsoft, Tesla, Amazon, and so forth. And then for their weights, I'm going to set a variable called weights equal to numpy.array. And that's going to be a list within a tuple, and the arguments are all going to be 10%, 0.1. In other words, there's going to be 10% of the portfolio in each of these 10 stocks. Control Enter to run that. Next, I'm going to choose the time period that I want to run the value at risk calculation on. So I'm going to start with January 1st, 2019 through the present. So how am I going to do that? I'll create a variable called start and set it equal to Delta Tango decimal date time with 3 arguments: the year, which is 2019, the month, which is January, and the date, which is the 1st. I'll create a variable called end, and I'll set that equal to Delta Tango decimal date time decimal now, and that's going to be an empty tuple with no arguments in it. In other words, it's going to choose today's date, January 16th, 2023. So we're running this at the beginning of 2019 through about mid-January 2023. And then since I have that list of tickers, I can download the data from Yahoo Finance. To do that, create a variable called D as in Delta, F as in Foxtrot. Set that equal to Y as in Yankee, F as in Foxtrot decimal download with 3 arguments: the tickers list that I created earlier, the start date, and the end date, which I also specified right above this line of code. And then I just want the adjusted closing price, so I'll create a list, and adjusted closing price will be the thing in it. And then to show that data, type D as in Delta, F as in Foxtrot. Control Enter to run this, arrow down. And you can see it shows the date and the adjusted closing prices, which adjust for dividends and stock splits of the 10 different companies in question. Keep in mind that we have 10% of our portfolio in each for this value at risk calculation. So you can see, for example, on January 2nd, 2019, Apple Computer had a adjusted closing price of almost $38.11 by way of example. Next, I want to get the returns, so that's easy. I'll create a variable called returns and set it equal to D as in Delta, F as in Foxtrot, decimal, %_ change, Control Enter, and that will have an empty tuple at the end of it. And then I'll just type returns, Control Enter to run this. And now you can see the daily log returns based on adjusted closing prices for the time period for each of these 10 stocks. Moving forward, I would need to create the variance-covariance matrix. Well, how am I going to do that? I'm just going to set a variable called cove_matrix equal to returns decimal cove with an empty tuple, no arguments, and then type cove_matrix, Control Enter, arrow down, and you can see the variance-covariance matrix. In the first row and first column, that cell is the covariance of Apple Computer with itself, which is just the variance of Apple. In the final cell in the lower right, it's the covariance of Tesla's returns with itself, which is just the variance in the returns of Tesla. To create a normal distribution for the covariance method to calculate value at risk, I need to know the average return and the standard deviation of that. So I'll set average returns, a new variable, equal to returns decimal mean with an empty tuple, and then I'll type average_returns. I'll press Control Enter. And you can see the list of average daily log returns for the 10 stocks in question over the time period. A little over 3 years of data. And then I want to count the number of data points that were used to calculate that average, so I can create a variable called count and set it equal to returns decimal count with an empty tuple and a list with 0 as the argument, and then type count. That way it only shows the data in question. You can see there were 1,016 data points over the period in question. Then I want the average return of the portfolio as well as the portfolio's standard deviation for a day. These are both daily returns and daily standard deviations. So I can use the average return function at weights, which I also created, and that'll give me a new variable I created called port_mean. That's the mean return of the portfolio, and then the mean standard deviation of the portfolio. I could do numpy decimal square root weights.t, the transpose of the weights, times the covariance matrix, times the weights themselves. Press Control Enter. Then to show these, I can see the portfolio average return for the time period of being questioned was about just under 15 basis points a day of return. Standard deviation was 2.15% over the time period in question, average daily standard deviation. And now with that information in mind, I can create the normal distribution. The horizontal axis will range from -0.05 positive 0.05 in increments of 1/1000. So I'll set the variable x equal to numpy.arange with only one R as in Romeo. So it's not a range, not like I'm arranging something, it's a range. And the three arguments are negative 0.05, positive 0.05, and 0.001. The norm distribution function, I can create that by integrating a probability density function with the arguments x is an x-ray, the portfolio mean, and the standard deviation. That's the beauty of a normal distribution. It can be fully described by the mean return and the standard deviation of that mean return. And then to plot it visually, I use P as in Papa, L as in Lima, T as in Tango, decimal plot with the arguments x is an x-ray, norm distribution, and a color of red, R as in Romeo. And then to show it, just P as in Papa, L as in Lima, T as in Tango, decimal show with an empty 2. That's the normal distribution. Now to calculate value at risk, I need to know the confidence level. So let's say I want to be 95% confident in my calculation. I'll set a variable called confidence level equal to 0.05. And I'll set a variable called value at risk equal to norm decimal P as in Papa, P as in Papa, F as in Foxtrot with the arguments confidence level of 5%, the portfolio mean and the portfolio standard deviation, and then type VaR to execute on that. And we can see the daily VaR. We're 95% confident based on this calculation that we will not lose more than about 3.4% of our portfolio in one trading day. Let's say we wanted this over 5 trading days. We could set a variable called num_days to 5 and do value at risk times the square root of the number of days, the square root of the periodicity, in other words. And in 5 trading days, we're confident at a 95% level that this portfolio is not going to lose more than about 7.6% of its value. And then on any given day, we can create 2 variables, lower and higher, which equals mean return minus 2 times the portfolio standard deviation divided by the square root of the number of data points. And then for higher, it's the same thing, but you add the ending part of the equation as opposed to subtracting. Then you run lower and higher. And you can see we expect our portfolio to trade. In a typical day, our portfolio will earn between 0 and 2% per day. Or actually 0 to 28 basis points per day. Sorry, I misread that originally. So that's how you run these calculations. Take this knowledge into the marketplace to be a better user of value at risk and Python code. Have a great day. Thank you for watching this video. Please subscribe to my YouTube channel, hit the notification bell, hit the like button, leave a comment below, and please buy my books. The links to those will be in the description of this video.